For more physics-related videos, please subscribe. Welcome to Stellar Physics 5b. In this video, I will go over nuclear stability and decay. This video directly follows from the previous one, Stellar Physics 5a, where I went over nucleosynthesis, so I highly recommend you watch that video before moving on to this one. I rated the physics level in this video as intermediate. So let's start off by reviewing what we went over in Stellar Physics 5a, where I derived what's called the Semi-Empirical Mass Formula. This is a formula for finding the mass, or the mass energy, of any nucleus with atomic number A and charge Z. The atomic number is the total number of nucleons in the nucleus, which means the number of protons plus the number of neutrons. So here we have A equals Z, which is the charge of the nucleus, so number of protons, plus N, which is the number of neutrons which have no charge. So I'm just going to briefly recap what the terms in this formula are, as I already derived it in the previous video. So as I said, this is a formula for finding the total mass of a nucleus. So what is that going to be? Well, since the nucleus is made up of Z protons and N neutrons, that's initially going to be Z times the mass of a proton plus N times the mass of a neutron. But these masses are the masses of protons and neutrons if they are free, meaning if they are not bound to a nucleus. But in order to bind these free protons and neutrons into one nucleus, you have to release some binding energy. The binding energy is simply the energy you'd have to put into the nucleus in order to break it up. So the rest of these terms sum up to the total binding energy. Just to remind you, what's binding these nucleons together is the strong nuclear force. This first term is called the volume term, and it's basically just saying every nucleus in here is bound by its neighbors, and since there are A nucleons, this volume term, is going to be some number, A sub V times A, the total number of nucleons. This term is called the surface term, and it's a correction to the volume term due to the fact that the surface nucleons don't have as many neighbors, so they're not going to be as tightly bound. This term is called the Coulomb term, and it accounts for electrostatic potential energy. What's holding the nucleus together is the strong nuclear force, but that's not the only force at play here. Protons all have positive charge, and like charges repel, so the electrostatic force, or the Coulomb force, is actually trying to blow this nucleus up. So it's competing with the strong nuclear force. Ultimately, if the nucleus stays bound, then the strong nuclear force is winning. But you still have to account for this electrostatic energy. The last two terms come from quantum mechanics. This first one is called the asymmetry term, and it has to do with the fact that the more different the number of protons and neutrons are, the higher the energy. So the lowest energy would be if you have the same number of protons as neutrons. So for example, in this situation, we have a total of 8 nucleons with 4 protons and 4 neutrons. But in this situation, we also have 8 nucleons, but we have 3 protons and 5 neutrons. And it turned out that this configuration had more energy than this one. This last term is called the spin coupling term, and it accounts for the fact that both protons and neutrons have a magnetic moment, so they're basically little magnets. And what do magnets like to do? They want to stick to another magnet with opposite poles touching. So that means that anytime you have two magnets paired, one up, one down, that's a lower energy state than if you have a free magnet. And what we found in the previous video was that if A is odd, you have one free magnet, and we called this our baseline energy. We called this energy 0. If A was even, you could either have an even number of protons and an even number of neutrons, and in this case, every single magnet was paired up to another magnet. Since here we had one free magnet and here we have 0, this configuration has less energy by a value delta E, which is just the energy difference between a free magnet and a coupled magnet. If A was even, but both Z and N are odd, so we have an odd number of protons and odd number of neutrons, then we have 2 free magnets. That's one more than if A is odd, and so we have an extra energy of delta E. So this term is delta E times this number little delta, which will either be -1, 0, or +1, depending on which one of these 3 configurations you're in. Now, the derivation of this formula was somewhat hand-wavy, so While it does do a pretty good job of finding the mass of nuclei, it's not super accurate. What's really important about this formula is that it will allow us to find which nuclei are stable and which ones are unstable. Again, it won't necessarily find every single one as it's not super accurate, but it does a very good job of predicting the general behavior and the general conditions under which you have stable or unstable nuclei. And that's what we're going to show in this video. In the previous video, I briefly introduced what's called the valley of beta stability. This is a plot of all the various nuclei with the number of protons on the vertical axis versus the number of neutrons on the horizontal axis. And these black dots are the stable nuclei. This is what's called the valley of beta stability. All of the various colored dots are unstable nuclei, and their color refers to the decay mode associated to their instability. So now we're going to use the semi-empirical mass formula to see if we can explain why this graph looks the way it does. So let's try to figure out what are the conditions for nuclear stability given the semi-empirical mass formula. First thing I'm going to do is I'm going to rewrite this formula. Notice that the way it's written now, I have three variables, A, Z, and N. But A equals Z plus N, so we only actually have two independent variables. The third one will be determined by the other two. So I'm going to rewrite this formula by replacing N with A minus Z. Now remember what this formula tells you. It tells you the mass of the nucleus with atomic number A and charge Z. So let's say we want to know which nucleus of atomic number A will be stable. Well, in this case, A is being held fixed. So the only thing that can change is Z. So how does this formula depend on Z? Well, the highest power of Z will be Z squared. Here we have a term that's going to come out to Z squared. And then when we factor this out, the third term will be proportional to Z squared. Then we have terms that are proportional to Z. So the cross term in here will be proportional to Z. The Z times -1 term will be proportional to Z. And then this term is proportional to Z. And all of the other terms don't depend on Z. So we can rewrite this formula one more time as some number alpha 1 times Z squared plus another number alpha 2 times Z plus another number alpha 3 times Z to the 0, if you will. And this equation is a parabola in Z. Now, what do we want to find? We want to find which nucleus with the given atomic number A will be stable. And the way we find that is by minimizing the energy, because that's the name of the game for nature. In this case, minimizing energy means minimizing mass, because mass and energy are equivalent. So we want to minimize this equation with respect to Z. So how do we do that? We take a derivative with respect to Z and set it equal to 0. And when you do that and plug in the values of alpha 1, alpha 2, and alpha 3, you get that the critical value of Z, which I'm calling Z star, is equal to alpha 2 over 2 alpha 1, and that's approximately equal to A over 2 divided by this factor, or times this factor, 1 divided by 1 plus 0.008 A to the 2/3. Now, there's a couple things we have to point out here. Z is the number of protons, so it has to be an integer value. You cannot have 1.5 protons or something like that. So the actual Z value that will correspond to a stable nucleus will be the closest integer value of Z to this number Z star. Next thing I want to point out, if A is small, this number here is going to be small. And so Z star will basically be A over 2, slightly less. So that means that for small a, meaning for light nuclei, we expect to have equal number of protons and neutrons, unless of course A is odd, then A over 2 is not an integer. So in that case, you would get 1 extra neutron, because this factor is slightly less than 1. However, if A is large, then this factor may actually be quite significant, and so Z star will be less than A over 2. And the larger A is, the smaller this factor gets. So that means that as you move to heavier nuclei, we expect that the stable nuclei have more and more neutrons compared to protons. Well, why should that be? Well, let's think about this. The nucleus is held together by the strong nuclear force, but the electrostatic force wants to break this thing up because it's repelling all the protons. So that corresponds to this term. But this term here, the asymmetry term, says that the lowest energy is when you have equal numbers of protons and neutrons. So there's a competition going on between these two terms. Or you could also think of it, there's a competition going on between the strong nuclear force, which is trying to hold the nucleus together, and the electrostatic force, which is trying to break it up. Now, if you have a small nucleus, then you don't have that many protons, so this Coulomb term isn't very large. And so this term wins. And so we have equal numbers of protons and neutrons. However, if you have a large nucleus, then you're going to have a lot of protons in this nucleus, and they're all trying to push away from each other. So this term, this Coulomb term, will be quite large. And so it's going to be favorable to convert some of your protons to neutrons in order to reduce this term, even though that's going to increase this term, this asymmetry term. Because the reduction in the Coulomb term will outweigh the increase in the asymmetry term. Or maybe an easier way to think about it is the electrostatic force is competing with the nuclear force. If you have a lot of protons, the electrostatic force is quite strong, and so it's favorable to convert some protons to neutrons to reduce that force, making it easier for the strong nuclear force to hold this nucleus together. If you're finding this video interesting so far, please like and subscribe if you haven't already, and maybe share it with a few friends. Okay, so I mentioned that this is a parabola. So if we graph this equation, the mass of the nucleus versus z, the number of protons, we're going to have a parabola that looks like this, and z star will be at the bottom of this parabola. Then, along this parabola, you will have various nuclei with different values of z. They all have the same value of a in this case. This green nucleus will be the stable nucleus. It's going to be the closest integer value of z to z star. And then these pink nuclei, they can exist, but they won't be stable. They're going to want to move down this parabola and convert into this green stable nucleus. And in a little bit, we're going to talk about exactly how that happens. But first, let's go back to this value of beta stability. We just found that the semi-empirical mass formula predicts that for lower mass nuclei, we should have equal numbers of protons and neutrons, and the larger the nucleus, the more neutron heavy it should be. Well, this line here, this diagonal thin black line, is the z equals n line. And remember that these black dots are the stable nuclei. If we go down here to light nuclei, we see that the value of beta stability, which is these black dots, lies right on the z equals n line. And as you move towards heavier nuclei, the value of beta stability drifts more and more towards the neutron-rich side, exactly as we just predicted. So now let's get into what happens with unstable nuclei. So let's discuss the various decay modes. The first decay mode we're going to look at is the case where A doesn't change. So we have that the semi-empirical mass formula follows this parabola in Z. And this decay mode is called beta decay. In this case, you're going from a nucleus with atomic number A and charge Z to a new nucleus with the same atomic number A, but a different charge Z, which has either increased or decreased by 1, because you've either converted a proton to a neutron or converted a neutron to a proton. The reason this is called beta decay is because it involves the emission of beta particles. Beta particles are just electrons and positrons. So it turns out there's a few different scenarios for beta decay. The first one is if A is odd. If you remember, this corresponds to delta being 0 in the last term in the semi-empirical mass formula, the term that involved the pairing of magnets. So, as we showed, we have a parabola, and the stable nucleus, which will be the green one, will be the closest one to this value of Z star. The pink nuclei are unstable. They want to convert into the green nucleus. So how do they do that? Well, let's take a look at this guy right here first. It has a lower value of Z than the stable nucleus, meaning it has one less proton than the stable nucleus. Each nucleus on this parabola differs from its neighbor by one proton. So this one wants to have an extra proton. So how does it do that? It emits a beta minus, and in the process, converting a neutron into a proton. So the way you want to think about this is by charge conservation. The total charge has to be conserved. So you've emitted a negatively charged particle. This is an electron. Since you've created a negative particle, you have to then create a positive particle in the nucleus. So one of your neutrons turns into a proton. On the right side of this parabola, we have the opposite problem. These nuclei are proton heavy. So I'm going to take a look at this guy here, just because if I do this one, the diagram is going to get a little bit jumbled. So this guy has too many protons. It wants to convert to the green nucleus, but first it has to convert to this nucleus, which is also unstable, which will then convert to the green nucleus. So it's got too many protons. So instead of emitting a beta minus, it's going to emit a beta plus, a positron, thereby converting a proton into a neutron. Now it turns out that in this case, there's actually two ways this can happen. Instead of emitting a beta plus, you can capture a beta minus. These two processes are completely equivalent. Either way, you're converting a proton into a neutron. Now, why can't the same thing happen on this side? Why can't, instead of emitting a beta minus, I capture a beta plus and convert a neutron into a proton? Well, in principle, that can happen. But in practice, in most situations, there aren't any positrons around to be captured. Most of the time, you're going to be dealing with a neutral gas, and the nuclei are always positively charged. So they're going to be surrounded by a bunch of negatively charged particles, electrons, in order to make the gas neutral. So while it's perfectly possible to have positron capture, in most circumstances, there are no positrons around to be captured. Now, I should also mention that anytime you have beta decay, the creation and capture of electrons and positrons will always be accompanied with the production of neutrinos, which I haven't drawn in this diagram, for the simple reason that they're not really relevant to what we're talking about in this video. Yes, they are important because they carry away energy, momentum, and angular momentum, so you have to account for them. But as far as understanding how nuclear decay works, they don't really add anything qualitatively to what's going on. So I'm going to leave them out. Okay, so what we found is that if A is odd, we expect to have one stable nucleus and maybe one or two unstable nuclei on either side of it. Why one or two? Why can't I just keep going up this parabola forever? Well, in principle, you could, but it turns out that if you move too far away from the stable nucleus, you start seeing different decay modes, not beta decay. And we'll get to those in a little bit. Okay, so that covers the case where A is odd. Now, what if A is even? In this case, we have two possibilities. Delta can be plus or minus 1. Now remember that this magnetic coupling term does not depend on Z, so it's going to show up in alpha 3. Well, that just amounts to shifting the parabola up or down along the vertical axis. So in this case, we're going to have two parabolas, one corresponding to a positive delta E and one corresponding to a negative delta E. In the A equals odd case, as you move down the parabola, you're changing Z by a value of 1. But in this case, when you change Z by a value of 1, you jump to a different parabola. Along the same parabola, the nuclei differ by 2 values of Z. I should say by 2 protons. Now there's actually two scenarios here. One possibility is that the closest nucleus to Z star lies at the bottom of the top parabola. Another possibility is that the closest nucleus to Z star lies at the bottom of the bottom parabola. So we have to consider both these situations. Let's start with this situation. In this case, this is our stable nucleus. This nucleus has too many neutrons. So just as before, it's going to undergo beta decay by emitting a beta minus, an electron, in order to increase its number of protons. Similarly, on the right side of the parabola, we have too many protons. So let's take a look at this guy. It's going to beta decay by emitting a beta plus, or capturing a beta minus. They're equivalent, so I'm not going to draw both cases. Now, what is going on with this guy here? This nucleus, it turns out, is stable. Why is that? It has more energy than this nucleus, which has the minimum energy. So why doesn't it convert to this nucleus? The problem is, if it underwent beta decay, it wouldn't move to this nucleus because these are 2 protons away. It would move to this nucleus. And this nucleus has higher energy than this one. So it can't do that. So in order for this nucleus to convert into this one, it has to emit simultaneously 2 beta particles. And this is called double beta decay. And while this could happen, it's very unlikely. So theoretically, this nucleus is unstable, But in practice, it's actually stable because its mechanism for decaying happens very seldomly. But it does happen, it has been observed. Now you might be wondering, well, what about this nucleus? Why isn't this one stable? Because it's also 2 protons away from the stable nucleus, or from the minimum energy nucleus. And if it were to beta decay, it would have to jump up to this parabola, and that's going to be higher energy. Well, actually not. It only looks like it here because I haven't actually drawn this super accurately. In reality, the gap between these two parabola is very small. So actually, most of the time, this nucleus is sitting at higher energy than this one, because these parabola are actually very close to one another. I've just drawn them fairly far apart so that you can actually see what's going on. Now, what if we're in this scenario? In this case, our closest nucleus to Z star lies at the bottom of the bottom parabola. And just as before, depending on if you have too many protons or too many neutrons, you're going to beta decay to get to a lower energy nucleus. However, now, it turns out we have 2 nuclei that would require double beta decay to move to a lower energy nucleus. So in summary, if A is odd, we expect to have 1 stable nucleus and maybe 1 or 2 unstable nuclei to the left and to the right. If A is even, we expect to have 2 or 3 stable nuclei. And just as in the case of A equals odd, we expect to have maybe 1 to 3 unstable nuclei to the left and to the right, and actually, in this case, we'll have 1 in the middle, as well as in this case where we might have 2 in the middle. That covers beta decay. Now, what happens if we move further up these parabola is you undergo other forms of nuclear decay. And what are those? Well, the first one is proton emission. This is when you start off with a nucleus with atomic number A and charge Z, and you pop off a proton. So that means that you lose a nucleon, so A decreases by 1, and since you lose a proton, your charge decreases by 1. So this corresponds to jumping from, say, this parabola to one of these parabola, or vice versa, because we were either going from A equals odd to A equals even, or from A equals even to A equals odd, since we're changing A by a value of 1. Another possibility is that you pop off a neutron. In this case, we're again changing A by a value of 1, so we're jumping from this scenario to that one, or vice versa, but Z stays the same, since we haven't lost a charged particle. A third possibility is called alpha emission, and this is where you pop off an alpha particle, which is a helium nucleus, which is 2 protons and 2 neutrons, for a total of 4 nucleons. So now we go from a nucleus with atomic number A and charge Z to a new nucleus with atomic number A minus 4, since we've lost 4 nucleons, and charge Z minus 2, since 2 of those nucleons are protons. So that also corresponds to jumping from one parabola to another, but in this case, you'll either go from an even to an even, or from an odd to an odd, because A is changing by 4, which is an even number. The final possibility is called spontaneous fission. And this is when your nucleus breaks up into 2 nuclei, both of which are larger than an alpha particle. So this generally only happens with very heavy nuclei, where basically the nucleus is so large that the strong nuclear force can't hold it together. The reason for this is that the strong nuclear force, while it's very strong, it's very short range, whereas the electrostatic force is a long range force. So if your nucleus is too large, it's going to exceed the range of the strong nuclear force, and the electrostatic repulsion in the nucleus is going to win, and the nucleus is going to break up. But now let's see how this fits on the value of beta stability. The black dots are the stable nuclei. If you have too many protons, then you'll be above this value of beta stability, and it will undergo beta plus emission or electron capture, same thing, in order to convert a proton into a neutron. So that's what these green dots are, beta plus emission or electron capture. If a nucleus is below the value of beta stability, then it's got too many neutrons, so it's going to undergo beta minus emission in order to convert a neutron into a proton. Now, those two scenarios correspond to when an unstable nucleus is not too far along the parabola or too far away from the stable nucleus. If you go to a nucleus that's far away from the value of beta stability, so let's say far away on the proton-rich side, you start getting these dark red dots. and that corresponds to proton emission. Similarly, if you're too far away on the neutron-rich side, you start getting these medium blue dots, and that's going to correspond to either beta minus decay or neutron emission. Why is it both? In reality, almost all of the unstable nuclei can undergo various decay modes. What's being plotted here is the most likely decay mode. So these medium blue dots correspond to nuclei where beta decay and neutron emission are more or less equally likely. But if you're really far away from the valley of beta stability on the neutron-rich side, you also have these red dots, and that corresponds to neutron emission. Then it turns out that if you're up here for heavier nuclei, and you move off of the valley of beta stability, you start seeing these orange dots. They do show up in a few other places, like here and here, but they're largely concentrated up here towards the heavier nuclei, and these orange dots correspond to alpha emission. And finally, if you have really heavy nuclei, you start seeing these dark blue dots, which correspond to spontaneous fission. So now what's going to happen if you have an unstable nucleus? Well, let's say you have a nucleus that's over here in this area right here. Well, it's going to decay into another nucleus, and if that nucleus is unstable, it'll decay into another one, and if that's unstable, it'll decay into another one, and you'll get this sort of pinball effect from one nucleus to another until you decay to a stable nucleus. Now I want to go over one more thing, which is the binding energy per nucleon. So this is going to be the total binding energy of a nucleus, which is just its actual mass minus the masses of the individual protons and neutrons. And since this is the binding energy per nucleon, this quantity in the parentheses is the total binding energy, so we just divide by the number of nucleons, which is A. And this entire number is going to be a negative number. If we plot the binding energy per nucleon versus the atomic number A, we get a graph that looks like this. So what you'll notice is that you start off with hydrogen, which is just a free proton, so it has zero binding energy. And as you fuse to heavier nuclei, your binding energy increases in magnitude, meaning it becomes more negative, until you get to iron 56. And that's the most tightly bound nucleus. After that, the magnitude of the binding energy decreases again. So your binding energy per nucleon is a less negative number. Meaning, to fuse beyond iron 56, energy has to be put into the nuclei instead of energy being released. So that's why stars cannot fuse past iron 56. Because prior to that, fusion in the stellar core is releasing energy, which is what's holding it up against gravity. But then once you get to iron 56, instead, if you're going to fuse to higher nuclei, you're going to take energy out of the star, and now you're no longer producing energy to hold it up against gravity, and the star collapses until it eventually explodes in a core collapse supernova. Okay, but this actually brings up an interesting question. Since nature wants to minimize energy, and all of these guys on the right of iron 56 have more energy per nucleon than iron 56, why are any of these nuclei stable? Why don't all of these nuclei decay into iron 56? To answer this question, I'm going to make a plot of the binding energy per nucleon for two different nuclei. So here we have a heavier nucleus that's going to be around here somewhere, let's say, and we have a lighter nucleus that's going to have less energy, so it's going to be closer to iron 56. And this nucleus would like to be down here because that has less energy. But it turns out that the energy curve between these two nuclei looks something like this. In the previous video, I explained that you can think of these energy plots as being completely analogous to a ball going up or down a hill. These two nuclei are stable, so they're like a ball stuck inside of a gully. This ball would happily move down into this lower gully. The problem is, there's a hill in the way. So unless it has enough energy to get up this hill, it can't get down into this lower gully. And ultimately, that's the answer to the question. But let me elaborate a little bit more. In Stellar Physics 5a, I mentioned that classically, in order to get into this gully, this ball would have to have at least enough energy to get over this hill. But in quantum mechanics, that's not necessarily the case. In quantum mechanics, it turns out that even if this ball does not have enough energy to get over this hill, there is a probability that it will just show up in this lower gully. And this is called quantum tunneling. The idea is that while this ball doesn't have enough energy to get over this hill, instead, it just tunnels through the hill and winds up in this lower gully, hence the term quantum tunneling. So what's causing this hill here? Well, sometimes you'll hear a sort of hand-wavy explanation which is this is the energy of the deformed nucleus. So in order for the nucleus to break up into two, it first has to deform itself, and the energy of that deformed nucleus is higher than the energy of the initial nucleus that wants to convert into a lower energy nucleus. That's a little bit of a hand-wavy explanation, but it kind of helps you picture what's going on. This extra energy between this gully and this hill here is called the activation energy. It's the energy you'd have to put into this nucleus to activate nuclear decay. Now, I should point out that this barrier, this activation energy, is present in every nucleus, whether it's stable or unstable. It's just that in the case of unstable nuclei, this barrier is small enough that there is a reasonable probability of tunneling through it. For a stable nucleus, while the probability of tunneling through here is not zero, it's exceedingly small. And that's basically the answer. Why don't these guys just decay down to iron 56? Well, if they're stable, this activation energy is large enough that the probability of tunneling through this barrier is extremely small. So this nucleus turns out to be stable. Now you understand, at least qualitatively, how nuclear decay works and why some nuclei are stable and others are not. If you enjoyed this video, please be sure to like and subscribe, and click the bell to be notified for the release of future videos. In the next video, I'm going to go over the general physics behind nuclear reaction rates. Thanks for watching.